All right, we're gonna start now. So, hey guys, welcome back. We're starting a new unit today. Now it's gonna be databases. We covered roots last time, so we'll do a quick review for that. But yeah, so just before we get into class, PA1 was released last week and it's due tonight. If you guys have any questions or anything about that, just see us after class and we can help you out through it. But some common stuff that people in past semesters have dealt with are like to take advantage of. You guys should take advantage of the demos. So we post YouTube recordings of every class. They're available on the Cornell App Dev YouTube, and it'll just show us like step by step going through routes and how to implement them. And it's pretty relevant to your actual assignments, so make sure to take advantage of them and rewatch them. Also, we posted a test case file on Ed Discussion, and that's going to be testing all the actual functionality that we want you guys to implement, including like the status codes, the actual routes, stuff you should be returning. So make sure to at least like run that once to make sure your code is like good and satisfying the requirement details. Also, make sure to save your Postman requests and collections. A big part of the assignment is actually testing your code. And the way we do that is through Postman, and we have examples of that in the demos if you guys want to see those. And then finally, writing documentation. We covered it briefly in the last demo. It's basically just like comments describing your code. We don't expect that much, just like one line saying like this method creates a post or this method deletes a post. You don't have to be too explicit. Just make sure we know we can follow what you guys are doing. And then, as I said before, follow the API spec. If you guys run the test case file, that should just guarantee if you pass the cases, then it should be following the API spec. So before we continue, any questions about PA1? It's due tonight. You guys can also use slip days on it. But yeah. Sounds good. So now we're going to get into the actual lecture. Okay, sorry. There's also a weekly feedback form. So once you guys finish PA1, I think there's also instructions on there to fill out this weekly feedback form. They're worth 5% of your grade. We just want to hear what you guys think of the course, about the assignment, any ways that we can improve, make your lecture or course better. So yeah, please fill that out. And then now let's get into the actual review of last week. As I said before, today we're going to be covering databases. Last week we covered the actual routes, which is what you guys implemented in PA1. So just to go over it a little bit, we touched upon the client server model. Basically, a client is any phone, laptop, computer, anything that you're interacting with the web with. And the servers are the other side of that. So the desktops with no screen, so to speak. Basically, if you guys see pictures of like Google, you'll see these big racks of computers. Those are usually servers, and those are the things that respond to our requests. So clients send requests on the internet, and then the servers take those requests, they do those functions that you guys implemented, and then they return a response. So diving more into requests, obviously, as I said before, they're initiated by the actual client. So that's probably your phone. They're sent to a specific URL, which if you guys did PA1 yet, you guys know that when you guys write a route, like I think one of the routes in the PA1 assignment was /posts. If you go to that and you send a request there, the domain would be like the local host part of it. The route path would be /posts, and the URL parameters, which are typically optional. If you're doing a GET request, that'll be specified in the request. There's four types of those. There's GET, post, delete, and typically we use post again for the actual updating. And that follows the CRUD methodology of create, retrieve, update, and delete. And then finally, usually in a post request, we send meaningful data in the body. So taking an example from PA1, when you want to create a post, we send information about the post in the body, like the username and the text. And then on the other side of that, the responses. So this is what you guys actually implemented on your assignment. So they're triggered by the request. So the server takes in the request, and then it returns like confirmation of the requested operation. So that's basically the response back to the client. Typically, they're accompanied with response codes. So 200 is going to be like the OK, 201 means created, 404 not found, stuff like that. And then usually they send back JSON data, which is just like the Python dictionary converted into JavaScript. And it'll be just like a request, but on the other side. So just to illustrate a little bit more, we have the client server model. So the client initiates the request, they send it over to the server. The server processes that request with the root. It does some data operations. In your case, in the assignment, it was like creating a post or modifying a post or something like that. And then it returns the actual response of that. And then when it returns the response, it sends it back to the client. So now a key thing that you guys did in the PA1 was that we stored posts and comments in a Python dictionary, which is good and all, but I'm sure you guys saw when you were testing the actual assignment, whenever you guys restarted the file, you would kind of lose all your data. So if you start out with a blank like posts dictionary, you run the file, you hit create and you add a new post. And then if you want to restart that file, your data would be lost. That post dictionary would be reset to like empty. So that's kind of the thing that we're talking about with data persistence. Whereas like your data doesn't get reset every time that you try to rerun the server or the server crashes or something like that. And the key way that we actually solve that is through databases. So just going more into depth about like what you guys did. So uh, you have your post dictionary. Actually, you have your key of 0. That's going to be your ID. And then within that, you have your values, your ID, upvotes, title, link, username. And all this is stored in Python. And that's what I was kind of talking about before. Whenever you run a Python file, that data gets reset. So if we go into some deficiencies of that, as I was saying before, stopping the server means any newly created posts or any modified data gets reset. It also does not scale efficiently. So when I start adding like hundreds or thousands or millions of posts to that, obviously things are going to start to slow down because your Python file runs in memory and your memory is going to be slowly taken up by more and more of that data. And then finally, there's no formatting efficiency. So in a Python dictionary, as y'all guys know, you can add basically whatever key and whatever value to it. And there's no like limit on what you can add. So going back to this example, if I wanted to add a new field called, let's say like name, like my name. So I'd add just like, I do the post and then open a bracket, say name, close the bracket, and then make it whatever value. That'll add it to this, but that's not actually useful data that we want to store, right? We only want to store these. So that's what I mean by no like formatting efficiency. There's no way of like preventing that in Python. So that leads us to databases, which is the alternative that we're going to be discussing in class. So the fundamentals of a database is that it helps us organize our data pretty much. And it allows us to put all our data in one collected place that's easily accessible, updatable, and you can manage the data easily. And they're usually implemented as a collection of tables. So if you guys ever use Excel or like Google Sheets, it's pretty much exactly that same idea, just on a bigger scale, where you have rows and columns, and then you have a name of a column, and then you can insert data below it. So you can see an example here. Basically, we have an ID, an ID column, a name column, an age column, and a hobby column. And then each of these have its own values. So for the first ID would be me, age 19, hobby music. Second is Tony, age 19, hobby running. And basically you can keep going like this. And the thing to keep in mind is that each column name has its own like name and specific data type. So if you guys look closely at the ID column, that's just an integer. In the name column, since it's surrounded by double quotes, we know that's a string. Age, again, is also going to be an integer, and then hobby is also a string in this case. And the thing is, we can enforce that. So if I were to come in and say name equals 4, we can have that database reject that query. Or if I went in to try to add like a new column where like, let's say post, if I try to add a post columns here, it just wouldn't let you do that because that's not a viable like column there. So that in that way, we can have each row containing like a set of column values, and each one represents a unique item that we specifically want in there. So getting more into this, as you notice, each row is basically an entry in the column in the database. And each row is identified by a unique identifier called the ID. And that's kind of why we wanted you guys to have a unique identifier in your Python dictionaries. That's why we had that global post ID counter where you can access each like specific post by its number instead of trying to go for like a value inside of it. So The reason with that is because problems kind of arise if you try to specify by like value. So let's say we add another entry and we're trying to find like a specific entry by the name, right? So what would happen if we have two entries but with the same name but different age and different hobby, right? There'd be basically when you search for it, you come up with two instances, and how would we know which one to resolve to? That's kind of the issue that happens like at this small scale, and also when you expand to like millions of entries, that problem is just going to persist. So that's why I usually keep an ID, which is like a unique identifier for each entry in the table. And then as you kind of notice, the IDs automatically increment. So the ID starts with 1, and then it goes up to 2, and then every new entry gets its own unique ID. Yes, and then this is just with a new entry. So at the bottom, we added a new one for Archit, age 20, hobby, playing with dogs. Then as you can see, the IDs of like removed elements, since my entry was removed, it doesn't get reused. And there's a reason for that. Because if we go to remove a piece of data, and then let's say we want to add it back in, or an even simpler case, if we have an ID, like an ID counter, so we get up to 4, and then we remove 1, how do we keep track of that 1 we just removed? Like to free it up. So basically, how do I know that 1 is now a viable ID without searching through the entire database and finding that? There's really no reason to have to be able to really do that, especially because integers go up to really large value. And chances are you're not going to be needing to like use a bigger like value to save that space. So we just don't automatically reuse it. And then one key thing to keep in mind is that a database is not just one table. A database is a collection of tables. So coming into this, if you imagine Instagram, and Instagram's database doesn't just have one table. It has one for users, it has one for posts, it has one for comments, it has one for messages, a lot of different tables, but they're all encompassed inside that Instagram database. So as you can see, each table will usually store different values. So in users, we have name, age, and hobby. In the post table, we have name, like description of like a post and the amount of likes it has. So in that way, we can kind of like separate our data into more meaningful like tables. And the key thing to keep in mind here too is that each one, you can see the IDs are repeated, but that doesn't really matter too much as long as they're in different tables. So in this case, we can still identify one entry as being unique, even though there's multiple tables sharing the same ID. And then just comparing this to what you guys did in the assignment, you can see that the database approach is going to be a lot cleaner. And it has a key, like it has an advantage of instead of restating like ID, name, age, hobby for every entry, we can just define it once and then have all of those below it. And that kind of saves a lot of space when you're dealing with large data sets. So just getting more into the benefits, as I said before, all data is structured. So if I go back, if I try to add something that isn't a name, age, or hobby, it just wouldn't let you, meaning it circumvents that Python dictionary like problem where you can just add random data. It also scales very well because we only need to implement or just add a new row. And usually databases are implemented in a way where it's like very efficient to do this. And then for actually querying data, so querying is just a fancy word for like asking the database a question. So if I ask the database who has ID 1, it'll return to me a Yush, age 19, hobbies and music. It's just asking it a question. And then the thing is, databases are really well like implemented to run this very fast and efficiently, which gets really helpful as we deal with larger and larger sets. So just getting more into the actual benefits. So if we were using the dictionary approach, as we showed you guys last week, this would be kind of the code to ask which users are over 18. So your data is just going to be a Python dictionary, users.json, and then we load it as a Python dictionary. And then we have a list of over 18 users. Then we loop through every single user, and then we check if the actual age is over 18. And then we append it onto a list, and then we return all of those users. So as you can see, this is kind of like clunky. It's not very like fast. If you guys took like basically it'll scale as the number of users increases, which is typically not a problem that we want to do, especially as these data sets get to like billions of users, because then this query will take a very long time. So our solution with that with databases is using a type of language called SQL. It's short for structured query language. Basically, we can write this one statement and it'll be exactly the same as running this code. So I touched upon SQL before. Its full name is structured query language. We shorten it to SQL or SQL, whatever you guys prefer. But basically, the main thing is it's a language for communicating with databases. So it allows you to like execute like creations or retrieve or update or delete very quickly through the database that you just implemented, rather than trying to like index it with like a Python dictionary. So for the actual creation of tables in SQL, this is going to be like equivalent to creating that post dictionary in PA1. We're actually just going to create a table inside SQL. So, or using SQL, sorry. The way we do that is by running the command. Anything you see in like full caps, those are going to be the actual like SQL commands. And then the lowercase ones are things that like you specify as the user. So to create a table, you say create table, you give it a name, then you give it the columns. So if I want to create that post table, before we would have create table name might be posts, and then we open the parentheses, column 1 might be ID, and the data type is an integer. Column 2 might be title, and the data type is a string, and so on. And this just allows us to format the actual data in our table. And so, yeah, just getting into an example that if we were to do a user, we create table user and ID is integer. I'll get into the rest of that after, but ID is an integer, name is text or string. We want that not to be null. So if you guys remember what null means, it's just basically the absence of a value. It's not like, it's basically no value. It's not like 0 or something, it just means there's nothing there. So we're making sure that name can't be null, age can't be null, and then email. It's similar to text, but it limits the characters to only 50. So there can only be at max 50 characters in an email address. So coming back to ID, we have integer primary key autoincrement. So integer, you guys all know, is just a number, positive or negative. Primary key is the thing I was talking about earlier about the unique identifier. So when we say primary key, it basically just means this is how we're going to refer to a value in a row in our database. So this is the primary way of actually like accessing that. So we say ID has the primary key, and then we reference each row by the actual number. Then auto increment is just like a convenience thing. So whenever we create a new row in our table, we just say auto increment. So the ID just gets added by 1 every time we create a new entry in our table. And then for actual insertion, we have insert into. Those are the key SQL commands. And then we give the table name itself, and then a bunch of columns, and then values, which is another SQL command, and the actual values. Just before I keep going further, it's not very important to actually memorize all of these SQL commands. We'll show you guys in the demo. The main thing is just to understand, like, we can use this language to create more efficient databases that allow us to create like faster applications. So yeah, getting into this insert example of this, one thing to keep in mind is that you can like omit the columns. So for the ID one before, if I was inserting into the name, age, and email fields, I wouldn't need to specify the actual columns, because it's like, it's given that like if you give 3 values, then you're going to be inserting into all of those columns. And then the thing to keep in mind is this is actually a bad practice about like omitting these columns, but you can if you have to. The thing is, like, this is not, first off, it's bad for readability, right? So like insert into table name, and then you give a list of values, but you don't know like where they actually go. SQL will figure that out, but it's bad for like actual humans reading the code. And then second, if the column order like changes, so in this case, if I were to put age above name, then the entire thing would break because it's not specifying like it would be trying to put like the age integer above into the name, and it would kind of break because name only accepts strings. So an example of that would be insert into user, name, age, email, and then the values John 21 JS123 at cornell.edu. And then for actually retrieving it, we have the select command. So select, and then you give a column or multiple columns separated by commas, and then from the actual table name. So as you guys can see, it's a lot like English in the fact like you can kind of just read off like exactly what you want it to do, and it'll kind of do it. A special case is if we don't specify the column names and we just want to grab everything from that table, we can just put a star, and that just equivalent to every column. And then from table name still applies. And then we can specify these as well. So instead of returning the entire table, let's say we only want like a certain condition. So this is going to be similar to like an if statement. So like before, when we we're trying to get everyone whose age was over 18 or 18 or over, we would select every entry from the user's table where the age is greater than 18. And that'll kind of like specify our query to actually return all of that. And then updating the data, this is just to modify the data. Again, the actual like syntax of this isn't too important. You guys don't need to remember that. Just like remember all of these functionalities that SQL lets us do. So update the actual table name, and then we set the new values of each column. And then we can provide a condition as well to only set those values for certain entries. So we update the user table, and we set the email equal to jsmith@gmail.com where the ID is equal to 1. So we get the entry where the ID is equal to 1 from the users table. We go in and modify only the email column to this new email. And then finally, the last thing would be deleting data. So if you want to delete something from a table, you do delete from, give the table name, and then where, and then the condition. Obviously, this would be useful like if you're just deleting a user. So like delete from user, right, equals 1. Again, the key thing to keep in mind is when you delete something, the ID is never reused. So once we delete user where ID is equal to 1, there will never be another instance of ID equal to 1. So yeah, any questions? Yep, and that was it for the lecture. Now we'll get into the actual demo of like concretely using a database. So
All right, what's good, everyone? So today for the demo, we're going to be working through the terminal, and we're going to be working with SQLite 3. I think of the pre-class to-dos, it said to install this on your computer. So that's what's going to allow us to, I guess, run these SQL commands in the terminal. So we're going to be using SQLite 3 again, and this is a tool built on top of SQL, and it basically allows you to like store a database in a file, which is really useful for, I guess, smaller projects. And then in real life, databases are stored in like very large servers, right? And they use the internet, but in our case, the databases are going to be stored in a local file. So yeah, to install SQLite 3, the instructions are in the textbook under the chapter 2 section. And in today's demo, we'll be creating a database showing the favorite ice cream flavors of the backend course staff. So the first thing we're going to do is run SQLite 3 in the terminal. And so we see that we have this little SQLite thing over here, and then we're going to be allowed to run SQL commands in our terminal. So I guess the first thing we're going to want to do is create some sort of table, right? Which is going to represent our database for today. Again, a database is not like one table, it's a collection of many tables, but just for today, we're just going to use one table. So let's create a user table, which is going to represent the core staff. So we're going to do create table user. And then what's really cool about SQLite 3 is that if you press enter, it's not going to end the query. To end like a SQL query, you have to use a semicolon. So I can just press enter and keep the query going, which is pretty nice. So I guess the first thing we're going to have or going to want to have in a user is some sort of ID that's going to like uniquely identify them. So we're going to have this as ID, and then we're going to have integer, primary, key, auto increment. So basically what, as I said in lecture, all these four keywords just basically mean that this ID field is an integer. It's your primary key. So it's going to be like your unique identifier that like identifies different entries in the database. And when it's auto incremented, that just means when a new user is inserted into this database, the ID of this user is going to be one more than the ID of the last user inserted. So if there was one user in this database and they have an ID of one, if another user is inserted, they're going to have an ID of two. So this is what all these four keywords do. And then for a user, I guess we're gonna want to have some sort of name associated with them. So we're gonna do name and then text not null. So the text is essentially like the string version of SQL, and not null just basically means that every user has to have a username. So we're gonna have a comma here, and then since this is like depicting our favorite ice cream flavors, we're gonna do favorite flavor. And this is again going to be some sort of string, right? So we're going to have text not null. And we're going to require that every like backend member does have a favorite flavor. We're also going to have favorite topping. And again, this is going to be text. No, sorry. Favorite topping is going to be a character of length 20 or yeah. And this is basically just saying that this is a string of length 20. And notice how we're not going to put not null over here. And we're going to show, I guess, later how, I guess, this can be used. And we're going to make, in having not null or not having not null in this instance just makes this field kind of optional in a sense. So then we're going to have a parentheses here, press semicolon. And so now there's no error popping up, which is good. So then the way we kind of see what tables are in our database is doing dot tables. And then we see that we have our user table over here. So now we have like a table, right? But we don't have any values in it. So I guess what we want to do next is like insert stuff into our table. Does anyone remember what the two like SQL keywords are for inserting into a table? It's two words. Yeah. So what we're going to want to do is, I guess, insert into this table, right? So we're going to do insert into table user. Again, we're going to specify the columns over here, which is good practice. So name, favorite flavor, and favorite topping. And then we're going to have values. Let's do me. My favorite flavor is cookie dough. And favorite topping is strawberries. Okay. So now we've inserted, but let's see how we're going to want to see this, right? So if we do select all from user, we see that we have one entry in here. It's me of ID 1. My favorite flavor is cookie dough, and favorite topping is strawberries. So let's insert another user into here. So I guess just do this. So we're going to insert a Yush. Say his favorite flavor is Rocky Road, and his favorite topping is let's say gummy bears. And then let's do one more user, but this time we're not going to include this favorite topping field over here, and we're going to see what happens. So values, let's say the person's name is Mateo, favorite flavor is vanilla, and favorite topping is, I don't know, chocolate chips. Oh, my bad. No topping. Okay. So now we select all from user. We see that we have three entries over here. We have me, we have Ayush, and we have Mateo. So notice how in Mateo's entry, there's no, I guess, field over here for favorite topping, right? I accidentally tried to type it in. And the reason why this kind of like returned an error, right, was because I only specified two columns over here. And we could do that because this field over here is, it can be null over here since I didn't have this not null field over here. However, let's say I tried to insert like another user with like no favorite flavor, for example. So if I try to insert a user simply with a name and have their name as like Caduce, for example, that's not going to allow us to do this because the not null constraint for favorite flavor was failed. So in a sense, every time we have a not null constraint over here, we have to supply this entry or this field for every given entry that we're inserting. So yeah. So now again, with the select query, we did select all from user, but we can also select like different columns, not just all of them. So if we do like select name and then like favorite flavor from user, we see that we have a name and a favorite flavor, but we don't have the favorite topping or the ID, right? And then also, if we try to access like a column that doesn't exist, so like let's say favorite smoothie over here, it says that there's no like column over here, favorite smoothie, right? So we have to specify columns that actually exist in this kind of database. So then let's say that my favorite topping suddenly changed from strawberries to blueberries. Does anyone remember the keywords, how to, I guess, update a table in SQL? Hint is I literally just said the words. Yeah, there you go. So we're going to do update table user. We're going to set my favorite topping. So favorite topping equals blueberries. And then what we need is like some sort of condition, right? So we need to identify like me as a user, right? So we could do where the ID is equal to 1. And so now if we select all from user, we see that my favorite topping has now changed from strawberries to blueberries, right? And so, yeah, finally, let's say that like I become lactose intolerant and I can't eat ice cream anymore because it causes some bad stuff. So again, does anyone remember how to delete a row from a database? I already just said the word again. Yeah, there you go. Delete from. Okay, so delete from table user where our ID is equal to 1. And so let's select all from user. And we see that I've officially been eliminated from this ice cream database over here. And then let's say that, I don't know, ice cream becomes poisonous and like nobody can eat it anymore. So let's say we want to drop like, I guess, the entire database. In theory, you don't want to do this because you lose like all of your data. And this is like if you want to delete your app or something. But the way to do this is to do drop table user, right? So if we hit this and then hit dot tables, we see that there's no tables showing up. So there's no like table user, I guess, in our database. And so, yeah, so that was the whole like demo for today. It was pretty short, but Wednesday's demo is going to be a lot more in depth and we'll kind of be showing you guys like, yeah, how to implement this for PA2. So, yeah.